Hi.
Hello. This week we're asking, how many dimensions does our universe have?
And the answer is either 4, 5, 10, 11 or 26.
Yeah, so the number of dimensions is simply the number of numbers that you need to specify where something is.
So if you take this point on the screen, for instance, you could describe where it is by how far along the screen it is and how far up the screen it is. Two numbers, so 2 dimensions.
Now, we're trapped in the 2 dimensions of your screen, but you're probably more familiar with 3 dimensions.
And in physics, even 3 dimensions is often not enough. We can measure the time that something happens as a 4th number. So we say space-time is 4-dimensional.
So it would seem that our universe has 4 dimensions.
But theoretically, there could be more hidden dimensions. For example, if you've looked into how to unify quantum theory with gravity, you'll almost certainly have come across this.
String theory.
Yeah, the idea is that fundamental tiny particles are no longer just dots. They're replaced by a strip of vibrational energy, or a string. Different vibrations in the strings naturally correspond to all of the different forces in the universe, making this an ideal candidate for a mathematical theory of everything. But when you try and do this in a way that's consistent with Einstein's picture of space and time, you find that it's impossible.
So it contradicts everything that we know through experiment then?
Yeah. Unless we build it in 26 dimensions.
26 dimensions. So this theory is either incompatible with everything that says that Einstein is right, or you need 26 dimensions.
Yeah, in 26 dimensions, everything works perfectly. Do you see? It's a theory that predicts how many dimensions there are.
Okay, for one thing, I mean, 26 numbers to describe where something is in space and time seems a little bit excessive. But, I mean, more importantly, you know, there's no fermions in here. There's no leptons, no quarks, no fundamental constituents of matter.
No, sorry, if you want matter in your universe, you will need this model.
Superstring theory. Well, it looks just the same.
Yeah, but this model has the fermions built in, and on top of that, the space-time in this model is much more stable. In the other one, space-time would tend to just spontaneously disintegrate.
Right, okay, well how many dimensions does this one have?
So that one has 10 dimensions, but I've also got M-theory. That M-theory has 11 dimensions, if that's more your sort of thing.
Well, which one's experimentally verified?
Well, well, none of them are experimentally verified. I mean, you can still have it on spec though.
Yeah, no thanks. Look, you see, as it happens, we have been looking for experimental evidence of extra dimensions at the Large Hadron Collider. But rather than hypothesizing a bunch of extra dimensions to make some crazy string thing fit with the known laws of physics, we've taken a different approach. We've taken the 4 dimensions that we know and love and have carefully added one more. So, for example, in the Randall syndrome model of space-time, the universe has 5 dimensions. But the particles that we're all made of are trapped in a 4-dimensional brane, as in membrane, much like that we're trapped in the 2 dimensions of your screen. Your screen is our brain.
All right, so that's much more testable then.
Well, yes, it is actually. So at the LHC, we create regions of very high energy in a very small space by smashing protons together. The idea being that we sort of punch through to this hypothesized 5th dimension and look for evidence that we've done so in our detectors.
I get it, yeah. So it's like this.
Well, no, you have to reach the specific energy of the higher dimensional resonance. So it's more like this.
Right, yeah, no, I see. So it's more like this.
Yeah, that's basically how we're looking for evidence of extra dimensions at the Large Hadron Collider. By punching through to the 5th dimension and looking for evidence in our experiments.
And have you found anything?
No. Which is why, for now, we're convinced that our universe has only 4 dimensions. Just as I said in the first place.
Okay, so just arrived in the post. Very, very excited. This is
String theory.
String theory.
String theory.
Obviously, this is the basic model. Doesn't have any fermions, but still
And
very.
Did either of those feature on Mark Chamkin's top celebrity inventions?
No, I don't think they did.
Not even
actually.
Stephen Hawking?
No, it didn't. But this is it. We're gonna unbox it for you now. So, it's quite a tight lid. Can't actually. It's quite hard to get into string theory, famously.
Yeah.
Here we are. So.
Okay.
So what we've got in the box. Got the quick start guide, obviously. Get started quickly.
Yeah.
We're already down to the good stuff. Got your open string there.
Yeah. Ooh, yeah. What would you use that for?
Yeah, well, that's electromagnetism, that sort of stuff.
Nice.
Then here is your closed string.
Yeah. What would you use that for?
That'll be for gravitons, you know, gravity things.
Flicking at people, maybe.
Well, no, because anyway. Also, you do have to watch out for this. Obviously, string theory does come. Oh dear, they make it easy today. String theory does come with a tachyon. That's a space-time instability.
Yeah. If you want to know more about tachyons, ask Greg Foot in Greg Foot Answers.
Greg Foot Answers.
He's your best bet.
Yeah. And then just at the bottom, subscribe to Head Squeeze.
Standard.